Barry Sharpless was born in 1941 in Philadelphia, Pennsylvania, USA. He was awarded a PhD from Stanford University, California in 1968, and is now active as professor at Scripps Research, La Jolla, California, USA. So please join me in welcoming Dr. Sharpless up on stage.
Introduction and ladies and gentlemen and friends and former students and colleagues out there too. It's a unique feeling. It's awe-inspiring to have two lectures that I, of course, understood every word of, but also that I couldn't have given myself because they're so beautifully organized. And that's my failing in life. I can't plan things. So some things need to be fixed up in the final written version of this. But I have some observations to share. What I really like to share is how the three of us were wisely chosen by this committee because we have the same spirit that we've evolved from our experiences over, well, in my case, a longer lifetime, but it's a profound thing to realize what you can do if you don't try to just do any old way of making molecules. And that's the main message I can give you. So I don't know, is this a forward and reverse thing too? Or okay, so yeah, this is the launching of click chemistry, and it started before there was any really motivation for knowing that it would work. But I did know that some reactions were better than others. And anybody who's been a chemist for years, like Morten and I have, know that you don't really have much faith in a reaction that's never given you more than 10-20% yield. Why would you consider using it in a plan? So even if you're planning your synthesis very carefully, there's only about a handful of reactions that good chemists would know, okay, I can go to the bank with this one, I think. Here's the way it started in, let's see, how do I push the laser pointer? Oh, it's right there. Okay. So this is where click chemistry started, in this old building which had pigeons in it and stuff, and we cleared it out and built some labs in there with Alfred Bader's funding. Alfred and Isabel Bader, well, Alfred, he was coming around to Dartmouth College even, and to Stanford with his patched elbow suit and his handing out coffee cups. And our generation knows who Alfred Bader is. Younger people, like I'm sure Carolyn never ran into him in that role, but he was the man who said, "What can I do for you?" Now, here's a man making chemicals for sale, and how many would go around door to door like that? But that's the way he was. And he started his lab in a garage in, I forget which city in the Midwest. And he was an important man who decided, and Victor Sneakus at Queen's College in Canada, he's indebted to Alfred too, because he endowed a big chair for Victor, who was another wonderful chemist who I've admired for years. And Hartmut Kolb is here in the audience, and Hartmut was the first click chemist because he came back from Ciba-Geigy when it merged. Had been a postdoc in the lab. He came back from Ciba-Geigy when it merged with Novartis, with whatever the other guy was, Sandoz, and became Novartis. And when something like that happens, the quality's going down. And Hartmut got out of there wisely, and he started organizing a chemical group, and he made hundreds of building blocks for chemists to have versatility in discovery chemistry. They thought these blocks were actually supposed to be small drugs or something in Japan. It just was ahead of its time. It didn't have any precedent for working. And so people didn't know what we were trying to sell. And somebody bought the company to make it into a drug supply line for their own new startup pharma company. So Hartmouth left again. And okay, now this is the man who made it possible for click chemistry. It may not be known to many people, but I couldn't get funded very well because I don't write grants very well, and I could never get funded for doing click chemistry. They hated it at the NIH in the study sections. They wanted total synthesis or complex very complex hammer and tong ways of making big molecules in those days. So Richard rescued me, he saw my potential, and he funded click chemistry. 90% of all the funding for click chemistry came from Richard's rich friends, and that he could constantly get to support his institute. My wife, on our 5th anniversary, well, she's the genius in the family. I won a Nobel Prize, but everybody knows she's the genius, and she names things like click chemistry and Sleeping Beauty, but her click chemistry is always stuck, and it stuck in the craw of a lot of people for years because it wasn't popular. It just didn't appeal to people. It seemed Mickey Mouse, and anyway. I can't say that I would be here today, or I would have been here the last time either, if it weren't for Jan. And I don't know where anybody's sitting. I get nervous, so I'll just say, oh, good, over there. Okay. Yeah, she keeps me connected to the real world. And besides also having really incredibly, she's a writer, and she's trained English major writer. Now, is this, I guess I don't know how to change this. Let's see. How do you make this? I can't get the normal thing to, what is it? Maybe I should start it again. Just go back and try to do it without the comments. Okay, then I go. Let's just go this way and see. No, it's going to go that. Okay. There. Oh, wait a minute. What happened? So I was born to be a process chemist. I was a fisherman from Norwegian, Swedish fishing family. My grandparents, and I worked on fishing boats until I was ready to go to college, and actually even while that time, before I went to Stanford for graduate school. And so I like catching things and interesting things, and also quantity was important when you were fishing for commercial reasons. So a process chemist, I'm not interested in little tiny scale reactions. I mean, I can do them and understand the meaning of them for analysis, but I want to make a handful of something, and so that I can do something, whatever I want with it, and just put it on the shelf as a reagent. So that's what a process chemist does. And so simplicity, my lifelong mission was to make things faster. I'm very impatient in the lab, and my son Will, he's here, who worked in the lab a year and a half, he's like me. We make things quickly, and they crash out, and we go on. And so the asymmetric oxidation got me interested in well, this is not quite written the way I would. Uh, it, the main thing about I learned came from George Hammett, a nonlinear thinker who was a professor and came back to work at Exxon for years. It's not making compounds that we're interested in. There's no sense to making compounds. There's too many of them. But it's the making of properties. You got to find properties. That's the magic of chemistry. We have properties all around us we haven't made yet, things that are easy to make. And that's what click chemistry has helped. Yeah. Now, this is why I'm disorganized probably, but the periodic table was very helpful to me. I dove into it as a kid in high school or even before in grammar school, and I read all about every element and its properties and does it react with water, or I just needed to know about everybody. And of course, a lot of these things you can't find anything out about. You go and look for things here you won't find. Well, cerium, these are okay. These are important today, and countries fighting over them. But the transition metals really set us off during my lifetime. But, I'm not so enamored of them right now. And copper, of course, is in Never Never Land here between the main group and copper is really, really special. It's very slippery. You can't stop it. It's everywhere in our body at attomolar concentration. And so there's plenty of copper if we can learn to house it better to do the chemistry that Carolyn and Morten would like to do even when the heart is beating. Elements in the table that I particularly have a relationship with is selenium. That came for an interesting reason. MIT, I thought I needed to write an NIH grant because I didn't think NIH grant would support chemistry. That's how naive I was. So I went out to Wisconsin for 2 months, learned from the experts on selenium biochemistry, came back, wrote an NIH grant, and then proceeded to discover that selenium was fascinating, simple chemistry, making olefins. So in 2 years of doing that on the side, it got me tenured at MIT. Okay. So Derek Barton was a friend and advisor to me. I liked his way of looking for new reactivity. And I was actually told by him I couldn't stop doing asymmetric chemistry if I wanted to win a Nobel Prize, which I thought was, I was Derek's point of view. And I was looking to get out of it because I can't stay on something very long. But went on for a while. Hartmouth came and we really did a job on the asymmetric epoxidation, dihydroxylation. That was probably the best reaction I've ever seen for catalytic oxidation. I put this in for those who, I'll leave it in the written version, and it just enumerates the events. Epoxidation was fine, and it sidetracked me with chirality. But chirality wasn't what I was interested in. I was interested in making efficient bonds. And I found out more and more the only bonds that matter are the bonds between things that are separate, like people. The first they get in the same room, maybe they hold hands, that's like Velcro. But then eventually, if you're wearing the right bracelets, there's a click, and then you're together forever. But when you put two things together, molecules, modules, that's where the properties come from. That's what nature teaches us. But we don't have the right to build things the way nature does, top down. She's making big molecules whose sole referential involvement is to control themselves and the other guys to make the right connections. And so, no, but we can start at the bottom. That's our privilege. We start at the bottom with a few things. Maybe we need a few thousand because we don't have all this massive territory we can cover, but we can come up from the bottom and make function. And that function can be affordable for hopefully much more people than biotechnology could possibly imagine being. Anyway, I made some enemies in this world. Enemies came heavily from saying the grail of carbon-carbon bond formation was perhaps a false grail, and I would defend that to this day, but let's not get involved in that. That probably set back click chemistry's acceptance for years. And MG came, he was a great student during the asymmetric oxidation and was the man who did the mechanism at MIT. But he was in Virginia, and then Richard Lerner loved MG when he was out on sabbatical, and he hired him as a professor at Scripps. And then MG and I got together, and we had, let's see now, like, I'm just going to jump to the end whenever I get in trouble, so don't worry. Overnight, so Richard, Richard loved this project too. It was the idea of, look, why don't we let the enzyme take 50 pieces on each side and do the cycloaddition, the azide Carolyn's thing, where you get this very weak, Wieskin, our hero, all of us, because of his great, physical organic chemists are much more important than people realize, and we didn't do them much good in the last 50 years, so I suggest we worry about them again in the future to help us. But so the enzyme can hold this thing together, and this cycloaddition could increase its likelihood. But it seems very pathetic because the concentrations we had of the pieces, and you'll see them in the next slide, this is what MG and I decided to do. That's our first article on the click. That's the manifesto that was written for click chemistry when we didn't even have a perfect reaction. So we were kind of making it up as we went along here, what might be. But we didn't have those reactions at that time. And where's my, no. Okay, this inspired MG and I, and Reza Ghadiri, a beloved colleague at MIT, bought a copy of Kevin Kelly's book, Out of Control. If you haven't read Kevin Kelly's book, you've got to read it. Even though it's written in 96 or 94, it's still relevant today to what life is, that a lot of us don't think of about life. And life is out of control. Of course, naturally, if it were in control, who'd be controlling it? And it would fail if it had some human controlling it. So Kevin Kelly says, nothing is more addicting than God games. He's got a chapter on God games. And don't get me wrong, these God games are not irreverent. Sim Earth, Sim City, whatever. But your first rule about God games that you learn is to be a God, you have to relinquish control. You set down your system and you watch it. Well, I mean, those games sound really hard to imagine succeeding. And so we were out walking on the beach at Scripps a few days later after reading the copies of the book Reza gave us. And we both said, well, what did you make of this book? What did you like? And we both loved the God game part because we realized there was a question where you could really see a problem. Because everybody takes x-rays of big molecules and they're sitting still, frozen to death with their mates at minus hundreds Kelvin. And then we make predictions about how we're going to stick something in this hole and other things we take. But it's like the ugly stepsisters trying to get into the Cinderella slipper. You know, they're breaking everything. And so humans are trying to design the finished product. Oh, you're stable in water, you could be a drug. That's really arrogant when you think about it. So what about if you let the molecule take a couple parts and somehow it can make a connection that's permanent? So the molecule can act as a reaction vessel, and that's, well, chemical space is big. This is something that everybody knows about today. I give Derek some credit here. I should mention Regina Bohacek, Colin McMartin, and Wayne Guida, who also had an elegant story on this, how the mass of the universe that we can see, the visible universe, could be occupied by one molecule of every possible drug that was less than 500 molecular weight, and it wouldn't be any matter left over to work with. So it's absurd how much stuff there could be. So my guess is about 99.99% of space close to us, 2 or 3 steps away, 4 steps away from things we could execute to have good, perfect reactions that could make a useful molecule strike into a real functional molecule. But that the screen is the problem. This is where I would say we should. That's my insight from the last few days. I thought, the biggest problem we have is screens. I mean, how are you going to discover? I have to stop, right? 10 minutes? Okay. Well, I got some extra time from the failure. Okay, thank you. So how are we going to screen for something? I don't know what you want out of a chemical. Everybody might have their own magic chemical interest for function from a human being or an animal. But it's how do you screen for that? You're not allowed to screen directly in humans legally, so that's a problem. But there are other things too, like how to make a building just overall have something that makes it last 100 years longer than it would for falling down. Corrosion in concrete, or you'll see what happened to me. Most of the chemists, we think about life, especially since Bertozzi put us into thinking about life as organic chemistry, which was a very misleading thing and absolutely absurd, of course. But that's okay. He did some great things for chemistry, but his own student Wohler proved him wrong, of course. From Germany, a postdoc. So here's the in situ with fancy Mike Peake at Scripps could make anything look great. Richard Lerner loved him. And this is the enzyme acetylcholinesterase. And here it is making in its guts, this thing that MG and I worked on together, making the triazole, clicking it together in its heart. And the inhibitor that came out was I'm going to have to jump over this one because what was the inhibitor? Why? Okay, maybe that'll come later. But the inhibitor was femtomolar, and it went down as low as 2 femtomolar. I mean, and this was the most potent inhibitor ever made from almost any enzyme, but let alone for acetylcholinesterase. So that was the first inhibitor we ever made in my lab, and it was made by MG and Warren Lewis and Luke Green. That was femtomolar. And that's pretty remarkable, from 50 pieces on each side. So there were a lot of combinations. The certainty of molecular chance. Well, when we started doing this assembly of modules, we found out we ran head-on into a problem. The best reactions that were out there were far from good enough. And here, I'll just show this slowly, quickly. Here's the quickest way we found, MG and Hartmouth and I working, and Jan in the last few days to figure out, because we had other ways of explaining this. But here, if I have a perfect reaction, what does it look like? Well, it actually looks like this. After 1,000, you can do this in the computer. You find this thing, you put it in, and it takes it to the power from 1 up to 1,000 or higher, whatever you want to do. So here it is. If you do 1,000 steps in a row with a 99% yield, and most organic chemists are going to go to the bank with this kind of a reaction. And in solid phase synthesis, Morten could tell me, they don't need that even, they just use excess reagent, right? And so 99% yield, this is what it buys you after 1,000 serial steps. You're down to 0.004. And then I come to 99.9, I get up to here. 99.99, I'm here, but to get to 99% after 1,000 steps, this is polymer chemistry, right? And here you have 99.99, usually helps to have another 9. And the thing almost never fades, and that's what this new reaction is like, and it's a polymer reaction. So, okay, let me just get through to that. This is the reaction that's magic and came into our lab with Dong. It's a suffix reaction. What happens is silicon, phosphorus, and sulfur love to change ligands with a suffix catalyst, and they do it as fast as the QAC reaction, if you can believe it. Room temperature, 130 degrees, it doesn't matter. The reaction doesn't even explode when it's done. Neat, and it's a polymer reaction. And here is the early team that published that, and Pongy's been working for a long time with me now at Scripps. He came back. He was a student who came back as a professor at Scripps, and we work on the polymer together. Here's MG, who's been involved in suffix chemistry and click chemistry from the beginning, almost. Hartmouth, of course, was really at the very beginning. Here's Jia Dong and Larissa Krasnova on this suffix chemistry. Now, what I want to show you is just how the polymer, you melt the polymer together, the two monomers crystalline, melt them together, and then you put the catalyst in, it makes the polymer, you put some more DMF in, you put DMF in, and then you pump it into a stirred solution. Jia here is showing, you get it crashes out in methanol, you wind it up, he called it bird net soup, bird net polymer. It's a beautiful polymer, very, very good fidelity. Okay, I know I'm running out of time here, but here you can see, no, I have no time, right? Oh, okay. So 500, here's another type we make from another gas from sulfur, the tetrafluoride. And this polymer is very, very easy to make. And it forms perfectly, and it has this extra spot where we put AZT out there with a connection through a QAC. And so we had this huge molecule with 500 thymidines on it. Every spot had a thymidine sticking out, and it was a helical structure. And if we didn't have this yield up here at 99.998, we wouldn't have gotten this yield. I'm sure this yield's too high, but even if it was 98, you can see the massive amount of yield you get out of this reaction. And here's the NMRs. The NMRs are ridiculous. This is a molecule with 500 units connecting, and this is the proton NMR, and this is the reference for fluorine. That's the fluorine at 500 megahertz or whatever the resonance frequency is, but it's just like one fluorine. And these got chiral centers in them, and they're helices. Here's what the thing looks like. Han Zuloff is our collaborator in the Netherlands, and his students got these pictures of these helices. The pitch of some of they know the pitch of them. Each of these will have like a nucleotide sticking out every turn. Its pitch is about 12 degrees. But the main point is that this is DNA, of course, and that's another nice polymer with sulfate, phosphates, affinities. But when you look at this from outer space and you come in and you're smart, and you're looking at somebody shows you that, you'd say, well, those are phosphates or sulfates. You can't tell by looking at them because they're either neutral or they have a -1 charge. Just to remind you that this chemistry that's helical is also related to life's chemistry. And finally, this is what I wanted to say. We ran head-on into an amazing thing. We've been trying to do biochemistry, but I never did polymer chemistry before, and I found it very hard to do. I didn't understand the arguments, and we got tremendous help from Molecular Foundry at Berkeley. And Carolyn used to run that Molecular Foundry. Can you imagine? She does she's a jack of all trades, I guess. But Yi Lu is a former student with MG and I, and Yi has been there for 10 years or so. And Pong knew him, and we got going. They would measure our polymers, our polysulfate polymers. And the main thing about these polysulfates is they are immortal. As much as you might say a sulfate looks like a weak wimp link, this thing is not coming apart in vivo. It's just stable. So it's just a connector. And here's what it does. If you make this polymer and then you use it to make these films, you just dissolve it in a solvent and make films, and you put those films on as capacitors. This was Yi and his student Henry's idea, because they had experience with capacitors under duress, under high heat and high temperature, and we don't have good ones right now. So what you make is sort of wrapped up coils of these films, and you wrap them around the zone where the horrible things are happening in a Tesla or a power station. If you have a capacitor, it has to load its charge and then wham, drop. And if it leaks, and you get heat, and you get so much heat that you can't function anymore, and the high field doesn't help either. They're both against you. So what we found was something amazing, I thought. This is one of the polymers we made, and we made it to have a high TG so that we could have a high temperature. And these are the gold electrodes, and the film that's laid down on those is our polysulfate film. It's clear, and then you wrap it around in so a way that you can run the field through it, and at 150 degrees, 750 volts, it gives the polysulfate is way up there ahead of all the ones used in electric cars now, or for any purpose where you need survival of this electric sort of. It's an insulator, but it holds the charge and then it drops it. Loads drops. So we ran it 50,000 times over 3 hours, and it just runs straight. There's no decay, and if we want, we can show that. They showed that if you wound it, then it makes a short, and then you do a few square wave cycles, and it comes back on a reproducible cycle, and it loses maybe 1 or 2% because it healed itself. It just burned up the part that wasn't any good, and now it's back to being a healthy capacitor material. So this was a complete intrusion into my life of physics, and I thought that was really a cool thing, because physics, especially physics with fields, right? Electromagnetic fields, this is magic. It's action at a distance. How the hell is this polymer? Well, we think we know, and how it's working. And we're after that now. And a man in Germany, Dietmar Stahlke, who's one of the few people I think understands main group chemistry, bonding, aluminum, silicon, sulfur, and phosphorus and sulfur. That's really messed up, that bonding, as it stands now in our life as chemists. So his way of looking at it, he can explain why this thing is not conducting. This phosphorus-sulfur linkages will resist conduction. There are no pi bonds. Most people, we all draw them as pi bonds. Oh, pi bonds. There are no pi bonds there. So that's the end, but I just had to get that last message out, that the certainty of chance, this is the certainty of chance that Jan wanted me to introduce, because I just, I can't get over how much chance, when you can make things quickly and you can test them against something reasonable, the certainty of chance is huge, right? I mean, do you intuit that? That's why I think it's important, that certainty of chance. And that's from a guy who was a jazz musician and the first person to say that he believed in the certainty of chance. He was I can't remember the Dadaist type movement, and the fact that life is one of the chances that we see here in front of us. Is one of the chances this universe offered, and it's occupied. Sorry for all the lack of order, but I just thought, humble thanks to all my wonderful students and postdocs and visiting professors and collaborators, and I'm going to get the names out there, of course, and a long list in the paper, but I couldn't get them together for today, so I apologize. But the ending was the main part of this story. It's certainty of chance again. Thank you.
Stay on stage. Okay. So we should stay up here. Okay, yeah. Thank you so much, Barry, for that fantastic and awe-inspiring talk. Right? And may I now call back Dr. Bertozzi and Dr. Meldal to come back on stage so we can all thank all three laureates for their fantastic lectures and accomplishments. You should come up. It's